Hello everyone, welcome back to the FTS simulation channel. Imagine a modern journey that's fast and comfortable. That's exactly what jet airliners offer. From their revolutionary debut in 1952 with the de Havilland Comet 1 to today's advanced technology, jet airliners have transformed the way we travel. But do you know what components inside an airliner enable it to take us around the world so effortlessly? With their massive size and weight, these planes are packed with numerous advanced parts and systems, from the frame, engines, and electrical systems to safety features and much more. In today's video, we'll dive into the details of jet airliners. Since this is going to be a very extensive discussion, you can skip to specific chapters by clicking the timestamps provided. Without further ado, let's get started. Airframe. For the exterior, we'll start by explaining the airframe. Here, we'll look at thousands of specially designed, durable panels, fastened using rivets to a lightweight foundation known as the aircraft frame. These panels and the frame are then combined to form a structure that is both incredibly strong and lightweight. Many of these components, particularly the outer panels, are made from carbon fiber reinforced materials. However, a significant portion still utilizes traditional aluminum and aluminum alloy materials. Next, we have the vertical frame. This vertical frame supports the tubular cross-section, which is connected by longitudinal frames stretching from the nose to the tail of the aircraft. Between these parts lies a vast network of stringers, intercostals, and subframes. At the nose of the aircraft, we'll find the radome. The radome serves to protect the antenna or weather radar located underneath it, while also allowing specific radio frequencies to pass through so the radar can function properly. Directly behind the radome, there is a double-layered bird strike barrier. Next, floor beams are installed on the frame to support the floor panels. High-quality panels are used in high-traffic areas such as the cockpit, while lower-quality panels are installed beneath passenger seating areas. 4 psi. In normal conditions, humans are accustomed to air pressure around 14 psi. Therefore, a pressurized bulkhead is necessary. This is a reinforced metal barrier that separates pressurized areas from non-pressurized areas inside the aircraft. This is crucial because when a passenger aircraft flies at an altitude of 9,450 to 11,600 meters above sea level, the air pressure drops to around 4 psi or even lower. As a result, most parts of the aircraft need to be manufactured to withstand pressurization during flight, ensuring a safe and comfortable environment for passengers and crew. These pressurized areas include the flight deck, passenger cabin, equipment bays, and cargo compartments. On the other hand, non-pressurized areas include the radome, landing gear bays, center wing box, and the tail section. On the sides, the wings are attached near the center of the aircraft. From there, the center wing box connects the wing structure to the fuselage. To provide additional support, a keel beam is installed. Additionally, the wing-to-body fairing is mounted on the keel beam and a pair of external longerons, which serve to cover and reinforce the critical wing attachment points. Next, the wing spars, which are both strong and flexible, extend from the center wing box to the wing tips, with one located at the leading edge and another at the trailing edge of the wing. From the wing structure, an engine pylon protrudes to support the jet engines. Titanium links extend from the wing to the pylon, while tension bolts connect aluminum and titanium plates, creating an exceptionally strong and flexible joint. Moving to the rear or aft section of the aircraft, the vertical and horizontal stabilizers are equipped with additional frame supports, while the tail houses the auxiliary power unit. Windows. Now, moving on to the windows, the aircraft's windshield and side windows are made from 3 layers of strong glass, protected by an anti-static coating. This coating helps keep the windows clean and shields passengers from external air conditions. The cabin windows feature thick outer panels made of durable acrylic material to ensure safety and provide a clear view. Additional acrylic panels are also installed around the passengers, equipped with small holes and air gaps to help balance pressure and temperature within the cabin. Doors. Now, for the doors, this aircraft is equipped with 4 doors. These include passenger doors located at the front, middle, and rear of the aircraft. Additionally, there's a smaller door behind the wing, which serves as an emergency exit and must remain in an inactive state. Activating this door would deploy the emergency slide. It's worth noting that opening an emergency exit door unnecessarily could impact public perception of the aircraft's safety. While such an event doesn't automatically indicate a technical issue, it may raise doubts among passengers unfamiliar with aviation safety protocols. Moreover, if poorly managed, such incidents can harm the airline's reputation, especially if the situation is sensationalized in the media. To maintain passenger trust, airlines often emphasize quick inspections and clear communication about the aircraft's airworthiness after such events. On the lower right side of the aircraft, you'll find 2 cargo doors. Looking more closely at the doors, you'll notice a lever that controls the door's opening mechanism. To open the aircraft door, the lever must be in the up position. If the lever is set to the down position, the door will open instantly, accompanied by the deployment of the emergency slide. Below the lever, there's an overpressure indicator light, visible both from inside and outside the aircraft. This light indicates pressure differences, alerting the crew to ensure a safe door operation. Looking even closer at the door's exterior, you'll find a ventilation panel, which helps balance the internal and external pressure. So, how do you open the door? By turning the interior lock handle, the door can be opened. There's also an exterior lock that can be accessed from outside the aircraft. As for the door mechanism, it operates on hinge arms that swing the door outward and away from the fuselage, with stabilizer rods guiding the opening and closing process. Wings and flight control surfaces. First, the wing itself serves to generate the lift required for the aircraft to fly. Its primary surfaces, however, control flight through components like the ailerons, elevators, and rudder. The ailerons typically move in opposite directions to tilt the aircraft, while the elevators control the pitch angle from front to back. Lastly, the rudder manages yaw, or the vertical rotation from the aircraft's perspective. Next, the entire horizontal stabilizer, where the elevators are mounted, can be rotated to maintain the aircraft in a specific position, while the elevators provide finer adjustments. To achieve this, the stabilizer is mounted on a motorized mechanism that moves up or down along a threaded rod. Secondary flight control surfaces. On the wings, there are leading-edge slats and trailing-edge flaps, which together form the high-lift system. When the aircraft requires additional lift, both the slats and flaps extend outward from the wing with a downward curve. This process not only dramatically alters the shape of the wing, but also increases the surface area exposed to airflow. As a result, the wing can achieve a steeper angle of attack, which is especially useful during takeoff or landing. Additionally, this change in wing shape helps reduce the risk of a stall. When the wing's angle of attack becomes too steep, airflow may separate from the wing's surface, causing a loss of lift and leading to a stall. However, with the slats and flaps extended and curved, the airflow remains attached, enhancing the aircraft's aerodynamic stability and efficiency. In other words, slats and flaps work together to ensure the aircraft remains stable and safe during critical flight phases, such as takeoff and landing. Their role in maintaining airflow and increasing lift makes them vital components in modern wing design. The curved slats are supported by a geared mechanism, driven by a shaft connected back to the slat power drive unit. For the flaps, a rolling flap carriage mechanism extends them outward, driven by the flap actuator arms. Meanwhile, the supporting flap track beams lower to adjust the flap's position. Additionally, at the rear of the wing, there is a row of multifunctional spoilers that assist the ailerons in controlling the aircraft's roll. Near the fuselage, specific spoilers operate in sync to create a lift dumping effect. This effect generates downforce during landing, helping the aircraft stick to the runway, slow down, and increase weight on the wheels for braking. Furthermore, along the wingtip and winglet, there are static dischargers. These are flexible metal rods designed to dissipate static electricity that accumulates due to friction as the aircraft moves through the air. Landing gear. The reinforced section of the wing is equipped with a mechanism for the main landing gear, which is typically stored within the wing and fuselage during flight. To deploy the landing gear for landing, there is a hydraulic retraction actuator attached to the main landing gear strut. During this process, the fairing doors rotate along with the retraction movement of the gear. When the landing gear is fully extended, the hinged side supports and locking mechanisms, each with their own actuators, keep the landing gear firmly locked in place. These components automatically unlock and fold together with the landing gear into its storage position. Additionally, the nitrogen and oil-filled struts also act as shock absorbers during landing, assisted by hydraulic dampers to reduce vibrations or shocks that occur when the aircraft lands heavily. This process ensures that the aircraft can land smoothly and safely. Each wheel is equipped with high-durability carbon brakes, consisting of rotors and stators. The wheel's rotor is locked with an internal locking mechanism, allowing it to spin along with the wheel. The stator is aligned with the axis and remains stationary. When braking, electric brake pistons press the stack of rotors and stators together, generating strong friction to slow down the aircraft. Furthermore, the nose landing gear is equipped with a slightly smaller tire than the main landing gear wheels. The braking system on this wheel is similar to the rack and pinion cylinder system used for aircraft steering. With this configuration, the aircraft's braking system not only ensures good control during landing, but also improves operational efficiency during flight. Engines. Now, let's explain the engine section. Of course, in the heart of the aircraft, the engine, there are several very important parts. First, let's start by explaining the core. The core of a jet engine is the gas generator that supplies high-pressure gas fuel to drive the turbine. This system includes the compressor, combustor, or combustion chamber, and turbine. Let's first focus on the compressor part. Compressor. The compressor in a jet engine operates by drawing air from the atmosphere and forcibly compressing it into a progressively smaller space. Each compressor stage consists of a rotating rotor, paired with a series of stationary stator blades affixed to the core casing. The rotor's role is to draw in atmospheric air, while the stator blades are designed to slow the incoming airflow and prevent backflow, thus increasing air pressure. Typically, a compressor will have multiple low and high pressure stages to achieve the necessary compression ratio, depending on the engine's design and technology. Now, let's move on to the combustor section. The combustor. In the combustor section of a jet engine, air is mixed with fuel and ignited as it passes through, with the fuel supply releasing a powerful gas stream. The design showcased here is an annular combustor, meaning it is ring-shaped. The compressed air enters through intake nozzles, each coupled with a fuel injector designed to distribute the fuel-air mixture evenly. Ignition devices, similar to those in car engines, ignite the mixture. Once ignited, combustion continues as air and fuel are supplied, much like a household gas stove. The turbine. Let's move to the rear. The turbine at the back of the jet engine is powered by exhaust gases from the combustor. Most of the turbine's power is used to spin the turbine fan, with a small percentage driving the compressor. It's worth noting that the turbine fan gets extremely hot. This issue is mitigated by diverting some air from the compressor to aid in cooling. Along with special coatings on the surfaces and a specially designed turbine fan to prevent direct contact with the hot gases, keeping temperatures under control. Exhaust cone. At the rear, we find the exhaust cone, specially shaped to mix and accelerate exhaust streams. Its working principle is similar to slightly closing a hose nozzle to increase output pressure. This part also serves to protect sensitive internal engine components. The fan. Originally, jet engines were turbojets, which directed all incoming air through the core. Most modern aircraft engines have evolved into turbofans, where only a portion of the incoming air is directed into the core or gas generator. This design allows part of the generated power to drive specially designed fans at the front. These fans, high-tech propellers within a duct, work by splitting incoming air into two paths, one into the engine core and the other bypassing the core, which is called bypass air. High bypass engines are designed for moving large amounts of air at slower cruising speeds, aiming for better efficiency. Moreover, the exhaust gas speed is a major factor in jet engine noise. Still, high bypass engines encase the fast-moving core exhaust with slower bypass air, resulting in quieter operation. Hence, these engines are often used in commercial or large military transport aircraft capable of carrying heavy loads. APU, Auxiliary Power Unit. The Auxiliary Power Unit, APU, is a backup power source that provides energy to various components of the aircraft, such as cabin air conditioning, cockpit avionics, and other needs when the aircraft is stationary and not connected to the airport's electrical supply. Additionally, the APU is also responsible for starting the main engines. The pressurized air generated by the APU drives a small turbine in the engine, known as the starting turbine. This turbine spins the main gearbox and the internal components of the engine, initiating the fuel and airflow processes that form the basis of jet engine operation, as we explained earlier in the engine section. As mentioned earlier, the APU is a gas generator that operates on a principle similar to that of the aircraft's main jet engine. Equipped with a battery-powered electric starter, the APU draws air through a port at the rear of the aircraft. This air is mixed with fuel and ignited, and the resulting combustion powers the turbine to compress more air. This process not only powers the electrical generator to supply energy to the aircraft's systems, but also provides pressurized air to start the main engines or serve other purposes. The exhaust gases from the APU are then expelled out the back of the aircraft, providing additional thrust when necessary. The APU also plays a crucial role as a backup power source for safety and comfort during flight, especially in situations where the aircraft is not connected to an external power supply. Fuel. The center fuselage and much of the wing area form a massive fuel tank system. This system consists of the left, center, and right fuel tanks, which together can hold up to 21,508 liters of fuel, weighing up to 17,400 kg when full. The ribs forming the wing structure not only serve as structural support, but also act as partitions within the fuel tanks. Each tank is equipped with baffles designed to control the flow of fuel and prevent excessive splashing. This is crucial for maintaining the safety and stability of the aircraft during flight operations. The system is engineered to ensure optimal fuel distribution, which is essential for maintaining the aircraft's balance and enabling efficient flight. How is the fuel loaded? Fuel is loaded through a port located in one of the wings. The fueling process is regulated by a fuel-filled Jach drain panel located in the wing fairing towards the fuselage, and this panel also displays the fuel level. To ensure even fueling, the automatic shutoff valves will open and close as needed. Once fueling is completed, the air inside the fuel tanks is replaced with nitrogen-rich air to reduce the risk of fire. This step is vital for maintaining safety during storage and aircraft operations. The exhaust valve from the main engine draws in pressurized air and directs it through an air separation module to reduce the oxygen content, leaving a nitrogen-rich product. After the air is separated, it is pumped into the fuel tanks. At the end of each wing, there are surge tanks that serve as vents for the main and center tanks. These tanks are also equipped with a NACA scoop, which forces air into the tank during flight, maintaining positive pressure within the fuel system while accommodating changes in pressure due to altitude and fuel temperature. This scoop acts as an exhaust air channel from the system during the fueling process. At the boundary of this tank, we will also find a one-way shutoff valve, ensuring that the fuel can only flow back into the main tank. The main fuel pump is located within the jet engine casing and is connected to the gearbox, supported by the jet engine to ensure a reliable supply of fuel into the engine. Each wing is equipped with small collector tanks that are always kept full to ensure a consistent and stable fuel supply during flight. To achieve this, a number of supporting fuel pumps work together to transfer fuel as needed from the center tank and the wings of the aircraft. These pumps, known as motivate flow pumps, operate using pressure alone, with no moving mechanical parts, providing simplicity and high reliability. Fuel from the main pump mounted on the engine is sprayed through a nozzle into a narrowing tube. This process creates lower pressure in the space behind the nozzle, resulting in strong suction that efficiently draws fuel into the flow. Additionally, electric boost pumps in each wing serve as backups in case the other pumps fail. During normal operation, the motivate flow pumps are responsible for transferring fuel from the center tank to the main wing tanks, then flowing it into the collector tanks before reaching the aircraft's engine. These electric boost pumps are available to provide emergency fuel supply if necessary, ensuring that the engine continues to operate smoothly even in emergency conditions. Transition. Anti-ice and fog. Hot exhaust air is used in the anti-ice and anti-fog systems. The perforated piccolo tubes in the wing slats utilize the hot exhaust air to melt the ice, which then exits from the rear of the slat. Additionally, the hot exhaust air is channeled through the engine front cover, which features small drainage holes at the bottom to optimize the expulsion of heat. For the cockpit area, the windshield and side windows are equipped with a heating film layer located between the layers of glass. This layer helps prevent the formation of fog and ice on the glass surfaces, ensuring optimal visibility for the cockpit crew. Hydraulics. This aircraft is equipped with 3 separate hydraulic systems to operate various critical systems. Hydraulic systems 1 and 2 serve as backups in case one fails, ensuring the operational reliability of the aircraft. Meanwhile, the third system, known as the Emergency Hydraulic System 3, is activated only in emergency and urgent situations. The basic components of Hydraulic System 1 are located in the wing fairing leading to the fuselage on the left side, while Hydraulic System 2 has a similar configuration on the right side. This placement is designed to ensure efficient distribution and reliability of the hydraulic systems under various flight conditions. Hydraulic actuators, often installed in confined spaces, operate various critical flight control surfaces such as spoilers, elevators, rudders, and others. Typically, multiple actuators control a single control surface, with each connected to a separate hydraulic system to ensure redundancy. Hydraulic System 1 controls actuators for upper rudder, left outer elevator, left thrust reverser, left and right multifunction spoilers numbers 1 and 3, flat power drive unit, left and right flap brakes, left and right ground spoilers, landing gear. Hydraulic System 2 controls actuators for center rudder, right outer elevator, right thrust reverser, right and left multifunction spoilers number 4, left outer aileron, nose wheel steering, slat power drive unit, left and right slat brakes. The Emergency Hydraulic System 3 can actuate the following: lower rudder, left and right inner elevators, left and right multifunction spoilers number 2, left and right inner ailerons, left and right slat and flap brakes, ram air turbine, air actuator, external lighting and antennas. For the lighting section first, there are navigation lights installed in pairs to enhance the aircraft's visibility. A green light located at the right wingtip, a red light at the left wingtip, and a white light at the tail. Then, there are flashing red beacon lights and white strobe lights to help the aircraft avoid mid-air collisions. Additionally, there are spotlights placed to illuminate the aircraft's logo, and side lights used for wing inspections when the aircraft is on the ground. There are also additional lights on the wing fairing leading to the fuselage and on the nose landing gear, providing extra illumination during takeoff and landing. Furthermore, we will also find taxi lights, which provide lighting around the aircraft when it is moving on the ground, ensuring safety and efficiency when operating in the airport area. On the other hand, for the antenna section, here we will find the weather radar antenna installed on the aircraft, which scans at various angles to detect and monitor the weather conditions around it. Additionally, other antennas are located on the fuselage, including the radio communication system that enables the aircraft to interact with ground stations, the anti-collision system to ensure flight safety, air traffic monitoring, the GPS navigation system crucial for determining the aircraft's position and direction, and the Ku-band antenna used for internet access and other data communications. So that's the exterior of the aircraft. Now, how about the interior? Crew areas. Here, we are faced with the crew area, which includes a front and rear galley equipped with foldable seats for the crew members. Structurally, we will see the flight deck door, made of sturdy materials with bullet-resistant inserts, and also fitted with a peephole made from bullet-resistant material. Additionally, at the front of the door, we will find a door latch designed to prevent the door from opening under pressure from the passenger side. On the side, a keypad is used by the flight attendants to request access to the flight deck, with an override code available for emergency situations. As a security enhancement, this area is also closely monitored by surveillance cameras to observe the situation inside the aircraft. AIR management. Next, air management. During the flight, pressurized air for the crew and passenger cabins is collected from both low and high-pressure compressors within the engine, which will then pass through the air exhaust valves, low and high-pressure air exhaust valves. This exhaust air is cooled by external air through the ram air duct in the wing, fairing to the aircraft body, before being routed through the climate control system for further processing as needed. A low-pressure ground connection is also available to connect the aircraft to an external air cooling source while on the ground. Furthermore, the air outlet pipe network connects this system to cabin controls at each seat and other areas of the aircraft. Inside the aircraft, there are balancing valves between pressurized compartments to maintain equilibrium, as well as outflow valves located in the pressure wall behind the forward cargo compartment. Water and waste. Next, for water and waste, this aircraft is equipped with 5 bathrooms, one in the front of the flight deck and the rest in the middle section of the aircraft. Additionally, there are sinks in both the front and rear galleys. The water supplied to the bathrooms and sinks is drawn from a tank with a capacity of 42 gallons or approximately 159 liters, located beneath the floor panel in the rear section. To prevent freezing, a heater surrounds the tank and the water heating pipes. The water heater near each sink circulates hot water through a mixing valve to regulate the temperature at the taps. Wastewater from the sinks is drained through waste pipes, which are also heated in the front and middle sections beneath the aircraft. This wastewater will flow and evaporate when the aircraft is airborne. On the other hand, waste from the toilets is stored in a waste tank and disposed of after the aircraft lands. In the disposal process, air and water are separated from the waste before entering the tank. For the separation process, at altitudes below 4,178 meters, a vacuum generator pulls the waste into the tank. However, when the aircraft is above 4,178 meters, the difference in pressure inside and outside the aircraft creates suction without the need for the vacuum generator. Electrical. Next, let's move on to the electrical system. There are two electrical equipment compartments located beneath the fuselage of the aircraft. First, the forward equipment compartment, which is located just behind the flight deck, and second, the central equipment compartment, which is located behind the wings. Both of these compartments are equipped with various electronics, computers, and other equipment that operate the aircraft's systems. Each engine is equipped with a generator as the main source of electrical power, while the auxiliary power unit serves as a backup power source. The distribution of electrical power is managed by three separate centers, supplying power to critical systems such as landing gear, high-lift systems, brakes, tire pressure monitoring, and more. In the forward equipment compartment, there are two main flight control computers, with an alternative backup flight control computer located in the central equipment compartment. Emergency systems. At the front and rear of the galley stations, there are first aid kits, flashlights, fire extinguishers, crew life vests, megaphones, and portable oxygen tanks that provide oxygen for 15 minutes to the crew members. For passengers, the oxygen generators above each seat row will activate if the cabin loses pressure, producing oxygen for about 13 minutes through a chemical reaction. The emergency locator transmitter will automatically activate if an accident is detected, emitting a signal to assist in locating the aircraft. The aircraft identification module provides specific data to the transmitter. Additionally, slide doors are stored in the lower compartments of each passenger and service door. When the door is opened, the slide will inflate and attach itself to the door sill. Meanwhile, the emergency exits above the wings are always ready for use, with rescue slides that automatically inflate from a special compartment near the back of the wing when the emergency exit door is opened. In addition, if there is a power failure, the ram air turbine, RAT, will automatically deploy and function as a small windmill, generating emergency electrical power from the aircraft's movement through the air. The power from the RAT is routed to keep the emergency systems, landing gear, and the number 3 emergency hydraulic system active. Additionally, a temperature-sensitive fire detection loop is installed around each engine and APU, equipped with spherical fire extinguishing bottles placed nearby. The equipment compartments are equipped with smoke detectors, while the cargo compartments are equipped with both smoke detectors and fire extinguishing bottles. The flight data recorder will record operational data for the last 50 hours, with storage capacity for 25 hours in a shock-resistant memory unit. This recorder is also equipped with an underwater locator beacon that emits a signal for 90 days. Furthermore, the aircraft health management system will store maintenance data and monitor conditions such as high winds, turbulence, and hard landings. Well, that's the discussion about the aircraft that we can explain in this video. As usual, if you have anything to add, suggestions, or feedback, feel free to write and share it in the comments below. See you in the next video, and thanks for watching.